Today we're going to have our second lecture on time series analysis, basically working on the ideas of decomposed time series and getting the internal structures of time series. So in the last lecture, you've learned basic concepts of data types, including section data, time series data, or panel data, which is also known as longitudinal data. And also you learned the idea about time domain and frequency domain. And also the frequency plot is known as either a spectrum or a power spectrum, which is known as a periodogram. And we also use the periodogram function to generate a periodogram using Python. Okay, so in this lecture, you will learn more about time series, including internal structures of time series, and how to degenerate a time series using Python. So we will using two methods. One is moving average method. The other one is a module called TSA. Right, so just recall what is a time series. So time series is a data set that varies as a function of time. And usually these time series data are equally spaced. So if not, and you probably need to do resampling, so make sure they're equally spaced in time and make your analysis a lot easier. So examples like time series, we've seen quite a few, so including like GDP versus year, sales volumes versus seasons, stock price versus day, and weather versus hours, right? It can be any time scales. For example, this is the daily mean temperature measured at Dallas from 1988 to 1991. And you can see that the temperature varies in different time scales in this way, right? So you can see that there's this yearly variation, annual variation, lower in winter, higher in summer. And they're also on top of this, and you can see these smaller spikes or faster time scales varies like weekly or daily or even monthly in this way, right? So in the time series, and we've also learned that in such a time series, you have different frequencies of variations, and those frequency information are given by a periodogram, right? And also look at this interesting time series, which probably doesn't mean too much, probably not too much physical information in it. So why is time series analysis useful? So the idea about analyzing a time series is to find the internal structures of a time series data and try to model it. So you can use either to do physical interpretations, or you can make predictions based on the internal structures of the time series. And this is what we're going to learn today. And we're going to learn the trend and seasonal variations and whatever is left called residual. Right, so as an introduction to the internal structures of a time series, so a typical time series data, YT, for example, usually have these four types of mathematical components. And the first one is called general trend, and the second one is seasonality, and the other two are cyclic movements and random variations, right? So most of these time series have one or more of these structures, as we just mentioned. So based on this notion, and a time series of YT is usually expressed as Y equals to T plus S plus C plus R, which stands for the trend, seasonal, cyclic, and random variations. Right, so it doesn't mean that time series must have all these components, but at least it has one or more than one of these components. So as you will learn from the rest of the lecture, and one objective of time series is to understand these variations and how to identify these variations. And all these varies with a particular frequency, and that's what we talked about in the last lecture, is that looking at the frequency spectrum or a periodogram of a time series and to figure out what's the variation period of the time series. So another objective of time series analysis is to decompose a time series into these components if they exist, right? So you can get the general trend, and you can get the seasonality, and you also get the random variations. So some of them are regular, some of them are not. So you can make predictions on the regular variations, and you can also see what happened in the irregular variations and correlate those with physical reasons. All right, so let's take a look at these components. So the easiest one to look at is the general trend, which is T here. All right, so the definition of a trend is a time series exhibits an upward or downward movement in a long term. So that's why it's called a general trend. For example, this is the CO2 data you've worked yesterday. Right, so this is the CO2 concentration versus month. So I have 160 months of data, which is about 14 years. And in this way, so you can see that the CO2 actually goes up in a periodic way, right? So this red structure down here going up from 330 all the way to about 345, and that's called the trend. So the trend is the long-term variation of the time series. Right. So the next one is called seasonality. So seasonality manifests as repetitive or periodic variations in a time series. So it's called seasonal, but it's not necessarily always means seasons. Right? Seasonal, it just means regular. So it has a fixed periodicity. So for example, you know exactly when a peak or a dip is going to occur. For example, in the CO2 data, so this little peak, so within 1 year, and we have a peak and a dip and goes back to normal level. So this variation within 1 year is called seasonality. And for the CO2 data, it's really relatively easy to understand because the CO2 level varies with seasons, right? So that's short-term variation, which is a 12-month periodicity, is called a seasonality, and it's regular. So seasonality means regular variations. Regular periodic variations not necessarily vary at seasons. All right, the next one is cyclic variation. So cyclic changes are movements observed after a few units of time, but they're usually less frequent than seasonal variations. So unlike seasonal variations, so cyclic variations may not have a fixed period of variations. So for example, this is the variation of CO2 by removing the trend and the seasonality. And you can see that I have ups and downs, up and downs, right? So some of them varies like every month, and some of them varies within like a year or so. So these variations are also have the periodicity, but they're not regular periodicity. So cyclic variation is different from seasonality because it does not have a fixed periodicity. All right, so if you take a look at this example of the time series data, which is the UK unemployment level, and you can see that in the past 40 years, and you can see that the unemployment level goes up and down in these ways. So all these variations, and they occur at different locations, and they have different periodicity. For example, this one goes up and down and lasts for about 10 years, and this one lasts for about 5 years. And then a much longer time later, and it varies another one. So these are cyclic unemployments, and they don't have a fixed periodicity. So if it's a seasonal variation, and we know that in winter it's going to go up, and summer it's going to go down, something like that. But for cyclic variation, you can't predict them because most of them do not have a fixed periodicity. Right. So another way of looking at these variations and is also that when we've talked about the three components, that trend, seasonal, and cyclic. So trend and seasonal, these are regular variations, right? The trend, you know, generally it's going up or going down, or it varies in a sinusoidal way. And seasonal variations are regular, they're just periodic functions, right? So whatever left is called the random variation, sometimes or irregular or unexpected variation of time scale. So in another way of defining a time series, which is the one that we're going to use in this lecture or in this course, is that when trend and seasonal variations are removed from a set of time series data, So whatever left, we call that a residual. So which may or may not be cyclic or may not be random, right? So random variations is that it's something that unexpected. So these are usually stochastic and cannot be framed in a mathematical model for definitive predictions in the future. Right, so that's the most difficult part, and you will see lots of random variations like that. So from here on, so we're gonna unpack the time series into trend, seasonal, and residual. So whatever is not trend, not seasonal, that's left, that's called residual. So these residual variations you can calculate using different ways, and we're gonna see how we're gonna calculate today using two methods. And analyzing these random variations, they're very problem dependent. All right, so to decompose a time series using Python, so there are two models. So one is the additive model. Additive model assumes that the time series Y is a superposition of a trend series T and a seasonal time series S and the residual variation R in this way, right? So the residual here is basically obtained after subtracting T and S from the seasonal components. And T and S are regular, so it's relatively easy to separate T and S from Y, and whatever left is the residual. And the analysis on the residual component is very problem dependent. So it depends on what kind of problem you're looking at. So there's no general way of how to analyze it. And the application is also different for different problems. And the other one is called multiplicative model. So multiplicative model is defined as when you have a time series that multiplies by the trend with the seasonal and the residual variations, right? So in the following parts, we will discuss the following two popular methods for estimating the trend and seasonal components. So when we got the trend and seasonal component, you can either using this additive model or the multiplicative model to get the rest of the components. Right, so we're going to look at the trend modeling using the moving average, which is based on pandas data frames, and also using another module in the statistic module called TSA, and use that to do the seasonal and trend decomposition in Python. Right, so how to decompose a time series. So we will talk about, first we'll talk about the moving average method. So the moving average, MA, at a time index, which is T, basically estimates the average trend component and is calculated by taking the average over the time period T plus minus K in this range. So K is the range of the moving average. So for example, at a given time T, I want to calculate the average from T plus K to T minus K and divide by the number of cells in this way, right? For example, if K equals 3, I call the window, the averaging window is 3. So it will be T plus 3, add all these together and to T minus 3 and divide by 7 in this way, right? So taking the moving average have an effect of smoothing the original data series by eliminating random noise. Right, so commonly the total number of observations K, M equals 2K plus 1, because I have K on this side and K on the other side, and plus 1, is used to describe the moving average as a M order moving window, and which is usually like this. So this is a order of 3. So this is a moving window of 3. So I'm taking 3 elements on the right-hand side and 3 on the left-hand side. I'm taking the average of 1 and give me 1 data point. So this is basically the moving window of doing the moving average. And then I move this star to the next one, I get another average in this way, right? So let's see how it works. So what's the effect of doing such a moving average by averaging K data points ahead of you and behind of you, right? So it actually smooths out variations with their periodicity smaller than the moving average window, right? So let's take a look at example with a moving average window of 9. So k equals to 4. So I'm taking 4 points ahead of me and 4 points behind me and taking average, right? So for example, let's take a look at this point at n equals to 5. So I want the moving average equals to 4. So I'm taking 4 values ahead of me, 4 values behind me, and I get an average here, right? So that's my average value. Okay, so now I move my window towards this direction. So let's say I'm moving my index to 10, which is this one, right? So I'm averaging this values in this little green shaded area. So I get an average value here because I have positive value 4 numbers here and negative 4 numbers here. So I get about 0. Right? So now we move on to, continue moving on to window 15, 20, 21, 22, 23, all the way go there. And when I move my window along this curve everywhere, so I get this red triangles. These are actually the moving averages down there in this way, right? So, oops, sorry. So what happened here, let's take a look at it again. So this is basically the average within this window, and that's the next window. And then I keep moving on here. So you can see that after I did this, and I can actually get something similar to a sine curve, but with the lower amplitude in this way. So what we did here is that when for this kind of wave time series structure, and we used a k equals to 4 window to move along the curve, and basically it reduces the peak of the curve in this way. And it does not change any periodicity or change the variations of it, just reduces the peak. So why is that? All right, so when the reason is that because the window is too small, right? So the window is too small. It does not have one single period to take out the variations. All right, so now let's take a look at another one with a moving window of 9. So k equals to 20. So I'm gonna take the average for every 20 points, right? For example, starting from 10, right? So I'm taking 10 points, 9 points ahead of me and 9 points behind me. So basically it's a one wavelength in this way, one peak and one dip. So what's the average of this one? With a window of 10, it's gonna about be 0, right? Because I'm averaging positive and negative about the same number of points, right? So now we move to the next window, right? Move to a couple of down here. And you can see that this periodicity is also averaged to one single number, which is also close to 0, right? So if you keep going, let's moving all the way down to the 53, n equals 53. So I'll be averaging this values inside this little green window. And you can see that because it's a full period of the sine wave, so the average is also about 0, right? So now you can see that when with a much larger window here, which is the window, now this window is exactly the periodicity of the sine wave, and I basically get a flat curve in this way. So it means that with a larger window, and you get almost a flat curve by just this moving average. Why is that? The reason is actually very clear, because when you're choosing a larger window and the window is larger enough to cover a whole one period or two period in this way, and averaging over such a period, you will get 0. So all the variations within this window is eliminated. So that's why after the moving average, you get almost 0 everywhere, right? So now you can see the importance of what moving average window to choose in this way, right? So for example, if you look at this smooth, this is a Python calculation moving over k equals to 10. So I'm involving every 21 neighborhood cells. I get an average. So this one is 10 cells from here, 10 cells from there, and that one is 10 from here, 10 from there. So I'm doing it as basically the sign variation is eliminated. So here you found that when I'm using k equals to 10, which is 21 neighboring cells, so the variation within the sine wave is basically eliminated, reduced, all the peaks are reduced almost to zero, right? So in this way, and you can see that you have to choose a window that is almost exactly what the seasonal variation is in order to remove these periodic variations in this way, right? So here's a quick question. Think about this. For a general data curve dominated by trend and seasonality, so how do we choose the moving average window, right? So the answer is very problem specific. For example, if the first thing I think you need to know is what's the period in your data, or what's the variation frequency or periodicity of the seasonal variations down there. So once you know that, and you know which window to choose, because you want to eliminate all the regular variations within that periodicity. So that periodicity of the seasonal variation is the window you need to use. Right, so how to do moving average using Python? So there are multiple ways to do it. So given that we have the equation, so the first one you think about is that you can use it using NumPy, right? For example, so this is a sine wave we generated in this way, and you can see that this is y equals sine 2 pi times t, and this is a simple for loop to do the job. So I set a window equals to 10, so I loop over all the i's in the y data, and then I'm averaging, basically use the NP, the mean function, which is taking the average of the points from index I minus window to I plus window and plus one. Remember that I plus window plus one is excluded. So I'm averaging from I minus window to I plus window. So such a for loop gives you the y smoothed data here, right? So once it's calculated, I'm using the red triangles to show the smooth data. So that's exactly how the average results changed. So in the, if you look at the lecture note, lecture 22 IPython notebook file, and play with the number of the window here, try to see if you can get a different periodicity and see what number of window is exactly needed in order to remove this periodic variations. All right, so there's another one you can use, which is in pandas, that's very handy to compute a moving average using just one function called rolling in this way. So the syntax goes data frame, that's the name of the data frame dot rolling. So you need a couple of parameters, but the first one you must have one is the window. So how many data points do you want me to do the running average in this way? Right. So there are other, minimum periods. These are all non essential inputs have defaults, and you can change them. And if you want more information about the rolling function, you can get it from the pandas documentation here. So let's take a look at the running average using the rolling function here to compute the trend in the CO2 data, right? So if you still remember that CO2 data, so here, what I did here is I created a new column called CO2 mean by using the rolling function, right? So what I did here is I took the column, which is the CO2, so that's CO2 is this blue curve, varies every 12 months, and I use the rolling function dot rolling and 12. So that's my rolling window. So why I'm choosing 12? Because my CO2 varies every 12 months. So that's my observation based on the data, the nature of the data set. Right, so rolling two. So how I'm gonna rolling it? I'm gonna roll it based on the mean. Right, so this rolling 12.mean does exactly the same job as what we did using the NumPy method in the previous slide. So pandas providing such a nice function that you can calculate this easily, right? So after you calculate this, so I plot the CO2 mean using a red color, and you can see this is basically the rolling, running average of the CO2, which each data point is a 12-month average rounding it. Right. So now next one, we can calculate the residual component after removing the trend this way. So one more thing. So when we look at this data, and this red curve is exactly that red arrow we showed, which is the trend, because in this way I'm basically removing the seasonal variations, and you can see that in general it goes up, right? Okay, so if we do another plot, which is the CO2 minus CO2 mean, so it will be subtracting the red curve from the blue curve, and you can see this is what's left, right? So you can see that this is a very more or less regular variation. It has a periodicity about every 12 months. So that's a seasonal variation of the CO2 concentration in the atmosphere. And trying to figure out why there's a seasonal variation in the CO2 concentration, it's a really good story. All right, so this is how you get the trend by choosing a running average window using the rolling method. So play with the window of the rolling and see that how does this red curve change. And so the key point here is to get the general trend. And you need to have a periodicity of the rolling that is exactly or very close to the periodicity of the seasonal variation. All right, so the other one, so the rolling method gives you the trend, and whatever left is basically seasonal plus the residual, right? So to separate the residual from that signal, as we showed in the previous slides, you need additional mathematical tools. And we're not gonna focus on that. You could either use a curve fitting to do that, but there are better ways to do it. So here we're gonna introduce another module, which is the last module of this course, right? So this is called statsmodel.tsa. So statsmodel is a statistic module that has lots of useful statistic analysis functions, and TSA is time series analysis. So if we use the function, it called seasonal decompose. So the syntax goes from stats.tsa.seasonal import seasonal decompose, right? So by doing this, and we can get it done, get the seasonal components, the trend, the residual components automatically using that function, right? So let's see how we do it. So first of all, we load the data to a pandas data frame. So that's the CO2 concentration data you've been working on since yesterday. And now we call the seasonal decompose function here. And the syntax goes seasonal underscore decompose data dot CO2. And here I use a function called toList. So what this does is that I'm converting the column CO2 into a list. You can also use a NumPy array or list that they all work fine. If you don't do this, and sometimes the seasonal decompose function may complain because it's seeing a series object, not a simple list of numbers, right? So I'm gonna decompose the CO2 column, and I'm specifying a frequency of 12, right? So remember that in the CO2 data, each data point is taken at 1 month, right? So 12 data points, that's 12 months, that's 1 year. That's exactly how a seasonal variation is, right? And model now you can choose either additive or multiplicative in this way. Right, so here let's try this multiplicative. So 3 inputs. One is the data column converted to list. And the second one is what's the frequency of the seasonal variation? I choose 12 here. And then third one, which model do you want? We use the additive model here, right? So once it's done, it's gonna return another object called result, right? So there are 4 components in the or attributes in the object result is result.trend, right? So if you print out the type of result.trend, it's a NumPy array. So you can use all the mathematical calculations or NumPy array calculations for this result.trend. So there are other three called result.seasonal, and you know that's a seasonal variation. And results.residual or resid, and that's the residual component. So that's basically by removing trend and seasonal. And mathematically, it could have both random and cyclic. Right? So results.observed, that's the original data sets. Right. So pay attention to the syntax here, and the most important thing here is choose the frequency of the seasonal variation. So the code knows how to decompose based on the periodicity. Right. So now if we do a simple plot like this, so if we do plt.plot results.seasonal, and you can see that I got a very regular variations, which has exactly a period of 12 months in this way. Right. So this is the seasonal variation that's separated. Right. So you can also use the plot function for the result object. For example, result.plot and show the plot, and you got 4 panels. And these 4 panels are exactly what we need, which is the original data called observed and the trend. And then the trend is basically the increasing CO2 level. And the seasonal is the very regular variations every 12 months. And also whatever left by subtracting the trend and seasonal from the observed, and that's called the residual. So it's a combination of random and cyclic variations. And you can see that there might be something going on at different time because of either the dip or a peak occurred when there's something happened there, right? So it's very problem dependent. So the seasonal decompose function is very useful by separating all these components of decomposing a time series. And then the key here is that you need to, before you use the function, you need to take a look at the data set and get a clear sense of what kind of seasonal variations are in your data set. So you choose the right frequency or right variation periodicity to use the function properly. All right. So this is basically the last function you will learn from this course. And of course, you will learn lots of other functions based on your own, because this, given the open source nature of the software and the Python community, and self-learning is always what makes you much better, make you improve in a way. All right. So let's go to the practice file and make some decompose